Hey, I am Mr. Allred, and I'm back, and I'm going to go through two formulas which are essentially the same thing. They are the growth decay formulas. Well, excuse me, growth decay functions. In the book I'm currently using, and even other textbooks, kind of have two variations of this. The first one might be for population. So it might be a model for how population changes over time. So the population after T years, or if we had a different situation, but we'll just say people population in the example, would have a starting amount times a rate raised to T. So we would have P sub 0 as a starting population. A being a rate, which is basically a ratio, and that'll be in decimal. If you're thinking about percent, you'll have to change it to a decimal. T will be time, I would say in years, but we could have other models. And P of T would be an ending population. And I mean ending by after time T. So like I said, you might see a variation of this, and it's the exact same thing. Usually it's dealing with radioactive decay. Okay, and usually there's not much of a radioactive growth. So radioactive decay, and it uses the exact same thing with just a different lettering. Excuse me, there I am trying to model the other one. So here, once again, we have a starting amount. So if we're talking about a radioactive material, we'd be talking about usually a starting weight. So grams, milligrams. We'd have a lowercase a, which again is a rate. T would be time, and depending on how radioactive something was, then it would actually could be like in minutes or hours, and then A of T would be like an ending amount. So basically, if we started with 5 grams of something and we decayed, we might end with 2 grams of something. So as you can see, they're pretty much formula for formula in these two. So we'll kind of work with what's going to happen. Now, what's kind of interesting here is here for the decay, that little a will be less than 1. Okay, it'll be bigger than 0 though, which means it would decay. So that means you would be keeping a portion of something. Over here with this A, I mean, it could be less than 1 if the population was shrinking, if there was a higher death rate than birth rate, or if people were moving away. But if the city was expanding, it could be bigger than 1. Okay, so just kind of keep that in mind. So let's kind of do a couple of examples, and we'll keep those close by. Okay. So let's say here, this is something similar to the book. It says, let's see here, in 2015, a rancher had 500 cows. In 2016, we'll make this easy. the rancher had, let's go ahead and make it pretty easy, 1,500 cows. And let's just say these all came from birth, so I've probably got something very unrealistic here. I doubt every cow had 3 calves. But let's see what we're talking about here. So we're going to use the population model. AT. So a couple things we know here. We know that time here was 1 year. And what we also know is that we started with 500 cows. We know that after that 1 year, we ended with 1,500. Well, what happened to our number of cows in 1 year? It tripled. So A would be 3. That would be our rate. So basically, as a function, this would be P of T equals 500 times 3 to the T. Meaning that we're starting with 500 cows in 2015, and what it looks like if everything follows the right exponential model, that we're tripling every year. So we could ask ourselves, how many cows will he have in 2020? Now, I have made up an example where you really do not want to mess with realism here. But if we started in 2015 and we're going to look at 2020, that would be 5 years. Okay. So all we have to do is plug in. So we will have P of 5 equals 500 times 3 to the 5. Let's see how crazy of an example I have made here. Yes, I've made something very ridiculous. 121,500 cows. So not realistic, but you can see what we've got here. If you were to turn this around and say that you had some type of disease and you had 500 people infected, and then the next year there were 1,500 people infected, then maybe you've got maybe a little bit more realistic model here. So in 5 years you could have over 100,000 people infected if it's an exponential growth. And with like some of the interest problems, we could be solving for, if we were given all the information, we could be solving for the initial population or the ending population. It's not that hard. So let's do one with the decay. Let's do a decay example. So let's say that we're going to start with, let's say, we're going to start with, we'll go with the nice number, 500 milligrams of a material. Okay, and we would say that after, let's say, 1 hour, we had, we're going to decay here, let's just say 250 milligrams. So we lost half of it. That'll be a fairly common scenario. But let's remind ourselves of the formula. A of t equals a sub 0 times the rate t. So this problem here, if everything was put in perspective, we would be looking at, we've got everything, the only thing we're missing here is little a. Well, what happened between 500 and 250? Well, the 1 hour here is very helpful, but it cut in half, which is 0.5. So we could write ourselves a little function, if everything holds, where we started with 500, and we're going to be taking half every hour. So we'd have to say here t is in hours. So maybe we could ask ourselves the question, how much is left after 24 hours, which is 1 day, right? So we're doing our formula, and what we're trying to find, since t is 24, basically we're asking ourselves to find a of 24. So let's do that. A of 24 equals, we started with 500, taking half of it over and over and over for 24 times. How much do we think will be left? Will it be much at all? Wow. Cutting in half really killed it. So another wacky example. Let's see here. So I started with 500 milligrams. So the number is coming out of my calculator is 0.0000298 milligrams. So this thing was giving off half of its material every hour. So you basically dividing by half, dividing by half, dividing by half. And what we get down to, if I've done this correctly, and let me type it in one more time to make sure. Yep. Is that it's virtually non-existent at that point. Okay. But that's a couple of examples using both formulas.